Hey all, today we're going to be talking about finding limits graphically. So limits graphically is kind of the intro. It's the first lesson with limits. So whatever you did last year, don't worry if you don't remember limits very well. I'm going to start all the way from scratch. So first off with limits is we evaluate limits not just as a number. A limit is not what the function is equal to, but what the function looks like it's equal to. It's what the function looks like it's approaching. So we read a limit that as x approaches some number, what y value does the function look like it is equal to or look like it's approaching? So to help evaluate this, sometimes we actually look at the limit from the left side or from the right side. So the limit as x approaches 1, and this little negative, this doesn't mean -1, but it means the limit from the left. Okay. Likewise, limit as x approaches 1 from the positive. Okay. It's not +1. It means from the right. And then the limit as x approaches 1 without the negative, the positive, is combining these two together. So I take whatever those two are, and I use both of them to evaluate the limit is at or as x approaches 1. So as it says, it will only exist if the limit exists from both sides and is the same. So if the left side, let's say, was 2 and the right side was 3, the overall limit would not exist. Okay? If the left side was 2 and the right side was 2, then the overall limit would equal 2. So we need both sides of the limit for the overall limit to exist. So as a couple of examples, limits kind of follow through a lot of our different rules of addition, subtraction, multiplication, and whatnot, just like any other function would. So if I have the limit as x approaches some number of f of x plus or minus g of x, that's equal to f of that number plus or minus g of that number. So we just plug it into both functions, add or subtract them together, whatever is being asked. If I have the limit as x is approaching some number of f of x divided by g of x, I'm going to evaluate f of x, and I'm going to evaluate g of x, g of that number, and then I'm going to divide them to get my limit. Okay, if I have the limit as x approaches some number of f of x times g of x, f of that number times g of that number. And then last but not least, if I have the limit as x approaches some number of f of g of x, remember this is our composite function, then I evaluate g at that number. And let's just say that g of that number equals, let's call it a. Then I evaluate f of a to get what my limit would be. So the composite one's a little bit weird because we have to do g first, and then we're going to evaluate f at whatever we got for g. So it's almost like two problems in one. But the general gist is you plug in the number, you evaluate the functions just like normal. So let's actually look at some graphical examples. We have the example over on the left. So we have a nice little cubic function, but right here in the middle at 1, we have that open circle, which if you remember from last year, that open circle represents a hole. So the limit as x approaches 1 from the left, what we're going to do is we're going to go from the left and we're going to follow our function. So as our function comes in from the left, what y value does it look like our function approaches? So as we get closer and closer and closer, our function looks like it gets to 2. So we say the limit from the left would be equal to 2. All right. Our other one, limit as x approaches 1 from the right. So once again, we do the same thing, but this time we come from the right. So we follow our function from the right. What y value does it look like it gets to? Once again, 2. So we say the limit from the right is also 2. Now, since the limit from the left and right were 2, that means the overall limit does exist and it is equal to 2. Now, conversely, if I ask what f of 1 is, so if I ask what the actual value of the function is there a point right here? No, there is not a point right there. So we would say undefined. Okay, just as a general rule, functions are undefined. Limits do not exist. Or D&E for us short math folks, because we like to write as few letters as possible. All right, let's look at another example. So we have g of x. We got a function coming from the left, a function coming from the right. The discontinuity we have going on here, think about it as if I was following my function to get from here to here, I was going to have to jump. So this is a jump discontinuity. We still have a hole, but we have a point that kind of comes in and fills in the hole in the track of the function. So the limit as x approaches -1 from the left, so we're going to follow our function from the left side. What y value does it look like it gets to? It looks like it gets to 3. So our limit from the left would be 3. The limit as x approaches -1 from the right, I'm going to follow my right-sided function. What y value does it look like it gets to? It looks like it gets to -1. Now 3 and -1, are those the same value? They are not. So that means our overall limit does not exist. So the left side and the right side were not the same, so our overall limit does not exist. And just like we said up above, functions are undefined, limits do not exist. Now, last but not least, if I asked you what g of -1 is, well, here at -1, while we have the hole, we also do have a point that's accounted for here. So if I were to plug x equals -1 into my function, I would actually get a y value out, and that y value would be -1. So just to kind of look at the two, if there's a hole and there's no point to make up for the hole, then the function is going to be undefined. If there's a hole, but there's another point to cover up for that hole, then the function is going to equal whatever the value of the point is. So let's look at another example. This time we have a nice function. We have a hole in the middle, just like we had in the first example, but now we just have a point floating out in space by itself. So our limit as x approaches 2 from the left. What y value does it look like we get to? -1. Our limit as we approach 2 from the right, what y value? The exact same one, -1. The left and the right side limit are the same, so that makes my overall limit -1. And then h of 2, okay, what do we have going on here? Well, we do have that hole, but we also have that point that makes up for it. So if I'm evaluating the function, I always go to the point, not where the function looks like it's going. So the point is at 2, so h of 2 would be equal to 2. Right, last but not least, we have asymptotes. So this is a good old-fashioned rational function. You did this towards the beginning of the year last year in pre-calculus. So we're going to be looking at this vertical asymptote right here. So as we approach the function from the left of 2, so as we approach the function, what's our function doing? Well, it's shooting up forever, right? It's going to keep going up and up and up. Well, what's all the way up at the top of forever? Well, positive infinity. So as we approach from the left, the limit is equal to positive infinity, right? As we approach from the right, same exact thing. So as we go up and up and up, what's it going to be? Positive infinity. Now, are these the same thing? Yeah, but does it kind of almost sound weird to say an infinitely huge number is equal to an infinitely huge number? Yes, so you can actually say infinity or D and E. College Board will accept both answers. So if on a test, there will never be both of those to try and trick you. They'll either put D and E or they'll put positive infinity. So don't feel like you have to decide between the two on multiple choice. And if it was a free response question, you could just put either and I'd accept both. Okay. Now J of 2, at 2, what's happening? We have that asymptote. Is an asymptote an actual point on a function? Nope, it's a spot on the function where we can't actually go. So J of 2 would be undefined. Okay. Then our limit as x approaches infinity. So which direction is infinity for x? Well, it's going to be out towards the right. Well, what y value does it look like our function is approaching as we go to the right? Now you might say, well, Mr. Arbona, it's going to keep going down. But what's there? There's a horizontal asymptote. Do our functions typically cross our horizontal asymptotes? No, they're typically guided by them. So if it just kept going, it's going to get closer and closer and closer to the horizontal asymptote without ever touching it. So what's the y value of this horizontal asymptote? 0. So we'd say our limit as x approaches infinity is 0. Now, conversely, as x approaches negative infinity, that's going to be out towards the left x values. Our function is doing the exact thing. So one thing to notice about rational functions is that as they go out towards positive or negative infinity, they're always going to approach their horizontal asymptote. Nice little fun fact. All right, on this one, we're going to sketch the graph and then find the values of our limit. So we have x squared plus 1. So we'll go up to 1. And it's just a nice little parabola. And yes, I realize that this is a quadratic function. We'll get to that in a little bit. And then I'm going to change my color for my other one. So we have x plus 1, nice little linear function, slope of 1. And no, do not feel bad if you did not know how to graph those. You will not need to graph things by hand for the AP exam. It is always useful to know how to graph things, but it is not necessary to know how to graph things. Okay, so those would be our two functions if we were graphing them fully, but what do we have? Well, we have a restricted domain because this is a piecewise function. So x squared plus 1 is only going to exist for values greater than 1. So what I'm going to do is I'm going to take away the rest of this for any values that are less than 1, and I'm only going to graph it for values that are greater than 1. So over there. Kind of just that little half of a curve. And then at an x value of 1, is this function actually able to equal a y value at 1? No, because 1 is not included in the domain. So right here at 1, I know you're probably like, Mr. Arbone, this is so small. We're going to put a hole for our parabola. Okay, now our linear line is for x values less than or equal to 1. So anything to the right of 1, I'm going to erase. So all of that, any values greater than 1, we're going to erase. We're going to keep everything to the left of 1 equal to that right there. And then this function is able to have a y value at 1. And that y value at 1 was 2. So I can put a point right there. Now, nice little fun thing that occurred. The hole that occurred on our parabola got filled up by the point for our linear line, which now means we have a point everywhere along our domain. So we have this nice little connected graph, which is cool and useful. But let's talk about what that means for our limits. So our limit as x approaches 1 from the left side. So as we approach from the left side, what y value do we look like we get to? It looks like we get to 2. As we approach from the right side, what y value does it look like we get to? It looks like we get to 2. Pardon my not really great graph. And then if the left and the right are the same, that means the overall one is 2. And our of 1, so you can look at the graph. We definitely have a point there. Even though there was a hole, the point covered it up. So the y value is 2. But if you don't quite trust me, well, let's just look at our domain. Which of these functions includes 1? Well, it's our x plus 1. So I can just plug that in. So r of 1 is equal to 1 plus 1, which is equal to 2. So sometimes it's nice to have nice little algebraic math back up our graphical math. All right, last thing I'm going to talk about with you in the notes is finding a limit from a table. So sometimes they might give you the information or the values of a limit from an actual table. So we have f of x is equal to x cubed minus 1 over x minus 1, a nice little rational function. And then they want us to find the limit as x approaches 1 of the function. So looking at our table, as we get closer and closer and closer to 1 from both directions, so 0.9, 0.99, 0.999, that's going to be from the left. And 1.1, 1.01, 1.001, that's going to be from the right. So as we approach from the left and the right, we're going 2.71, 2.9701, 2.997, and then 3.31, 3.0301, 3.003. So if we were just to take a guess, what Y value would you probably think we're getting close to? Well, hopefully you're thinking we're getting close to 3, okay? And you'd be correct. It looks like we're getting really, really close to 3. Now, as it says over here on the right at 1, what's happening? Well, more than likely, looking at our function, we probably have a vertical asymptote or a hole occurring right there at 1. I'm not doing any actual division or anything, so I don't know which one it is, but we probably have a vertical asymptote or a hole, which is why we're getting that error right there, which is why it's saying this method is an approximation. We don't have a graph to confirm it. We don't have an actual point there to make it nice and easy and get a value out. But looking at the data we have, we're probably pretty sure it's going to equal 3, which that's really the usefulness in a limit, is that even though we don't have a value there at 1, we kind of have a pretty good feeling of where the function is going to go. So a limit's a nice way for us to approximate the value of a function without actually knowing what the value of that function is. Okay, so fill out the rest of these notes on your own, y'all, and then you're going to be working through the limit stations today in class. Thank you for your time.